Hi, I'm Ed Sperling. I'm the Editor-in-Chief of Semiconductor Engineering. I'm here with Ken Wagner from PMC. We've heard a lot about power and the need for power in mobile devices, but there's another big push which is going on in the enterprise space, the data centers, the cloud providers. What's happening there? What's the big focus and what's the big problem?
Yes, Ed, you're completely correct. For the last 4 to 5 years, companies like my own have made major investments in power reduction because they're often limited by enclosure power limits, as well as the expectation from their customers that the power for the next generation will be as good or better as the power of the previous generation, while doubling, tripling, quadrupling throughput and adding features. And so all of those, we've got a perfect storm, if you like, of effects where power has now become essentially the number one constraint in some areas, in areas like non-volatile memory controllers and rate controllers and devices of that nature, as well as in the transport space, where traditionally the power has not been a particularly big issue, except for the making sure that thermally the package was lower enough cost that it did not require a fan or a particularly expensive heat slug for the lower ASP type devices. So now we have a new game in town, if you like, of trying to reduce power substantially above and beyond what moving to new processes could do for us.
So Ken, what are we looking at here?
Okay, well, I've tried to flesh out a little bit what the type of thinking that we have from conception through implementation of a chip that and a system that needs to meet a particular power concern. In truth, we often have contracts where, with some knowledge of the previous generation of device, that assertions are made in the contract about that the power levels will not exceed a certain level for that particular tier 1 customer. So how do we get there is the question when we're making some assumptions, perhaps well before we have the implemented device and the models associated with that implemented device, where we can be much more accurate with respect to the power. So as we mentioned in the earlier part of the discussion, mobile, what I would call big iron, the large multi-core processors, and pluggable devices such as our own, all require power analysis and power management. So we've got contracts, we've got packages, we've got enclosures like the PCIe slot at 25 watts where many devices must fit, and a particular chip or chip with DDR memory on a package must only consume a portion of that. They don't get the whole BOM power as well. So as we mentioned, that regardless of the fact that it's the next generation, we still need to meet those fixed power targets. When we talk about power, we talk about the power over a cycle typically, which is, we may talk about typical power across the range, we may talk about thermal power, or we may talk about peak or max power in the 3 sigma limits of the process. What is becoming a big issue, not only for mobile devices, but in the areas of data centers for utility costs and so on, is average power. And average power is obviously a variable that's much harder to calculate because it requires you to know your traffic situations and to be able to integrate them, if you like, over to find the energy over a large period of time.
In average power, though, typically you have a max and a min, right? Even with that average, because you can only go so much in a data center where you're saying, okay, we're going to run this so fast and we now have all these users coming in and we can't go above that. And you also don't want to have everything turned on and be so low that your utilization is very low.
Yes, I think that that's a good point. In spite of the fact we're calling it average power, it's really the power associated with different scenarios of operation. And so obviously there will be a range of average powers depending on what the workloads are. An interesting case in point might be something like forward error correction in a flash controller, whereas flash memories age, they tend to produce more errors per for their particular block, and as those errors need to be corrected, it takes longer to correct them. So therefore, for any one transaction, you have a longer period of time, and hence a higher power overall to get the job done. So average power will have a range, and that range is very dependent, it's very dynamic and very dependent on workload. There, as we mentioned as well, we have some power limits that we need to meet if enclosures and cooling are in the mix. Generally, cooling is passive cooling. Obviously, most customers would prefer not to pay for fans. In data centers, unfortunately, or fortunately for the data center owners, which are located often in cold environments, they are trying to operate at the highest temperatures that they can without having to have active cooling, again to cut their costs, which makes it harder for chip and system manufacturers to sell to them, because all of a sudden operating at higher temperatures can often aggravate the power situation with respect to the thermals of the chip. So at the architectural level then, as we look at essentially modifying the architecture for the next generation of devices, we need to make some power estimates. And what helps us there is that we have some reuse. Obviously, in some cases, at least at a subsystem level, we have previous experience with the power associated with those subsystems. And then we have some scaling. We know we've doubled the number of buses, we've doubled the number of SERDES running at a particular speed, and they haven't changed. We've moved one process, we know how those processes scale and so on. So we can make some power estimates at the architectural level, although they're not going to be spot on. Okay, and one has to realize there are some error bars associated with those processes. Then we're going to take those the determined architecture, and we're going to essentially mix and match or assemble the analog IP that's been developed or is already developed in that process for our device or our multi-chip, multi-die package. And whatever reuse we can gain in terms of productivity, obviously we want to leverage that as well, exploit that. And then there'll be, of course, some new development and some work to assemble the entire unit. At that point in time, we're in an implementation phase where we have to take all of this logic, both analog, mixed signal, and digital, semi-custom analog as well, sometimes some interesting technologies, and implement that at the physical level, verify it. These are tried and true implementation flows. However, there has been a tremendous amount of power savings over the years, especially in the last few years, in terms of understanding how to implement and save power.
Where are you seeing the worst problems?
I think we see some serious problems in several areas. One is in general AC noise issues on devices. Where traditionally we have had LDIDT plus RI being the overall expression for the delta voltage on a chip. When we characterize the timing corners on a chip based on the entire power system and power system management, we know that, or we bet that we won't go below or above a certain level. And AC noise can be very volatile. In new processes, the filler cells that provide the bulk of the decap capacitance, which supplies current in a transient situation when the regulators cannot, are often fleshed out. Well, they can be in a situation where that noise is very high. Those bypass capacitors are not capable within the time required to really fill the IFT or the DIDT noise, fill in for that. And so the voltage starts to drop on the device. And that voltage drop may go below the limits that we've postulated for that device. And that's a bad thing, obviously. This can happen for various reasons. It can happen because there's a lot of simultaneous switching on the chip, which is often due to large cross connects and is very data dependent. It can happen because of inrush currents on sleep modes. It can happen because of power gating inrush currents, mainly starting up, but there's a bit of a shutdown in Russia as well. There are some tools on the market that address the analysis of these situations, but I do anticipate, and we do see, that this is an area that we have to pay more attention to in the future.
Is it a question of the tools, or is it a methodology issue that you're grappling with here?
I think it's a combination of better. The tools exist, but the tools are people tend to avoid the tools because they are very complex. It is very difficult. You need the package model. You need models for the. Essentially, what you're looking for is the transient current behavior on the die, and that is very hard to derive. Okay, and it includes the power grid, the package, and so on. So people have had a tendency to try and take shortcuts in those areas. It's not really a tools problem. It's more one that there's only so many things that developers can address at the same time, and of course you go after the latest squirrel, if you like. And this is one of the latest squirrels, I think, in power management. The other one is that I'd like to point out is, as we go through this situation, and we've got a chip or a die defined or multi-die package, and really what we have to do is put through traffic scenarios. We need real traffic, just as we do in real measurement in the lab in order to determine power. We need to early on figure out our traffic scenarios, our power and sleep states, all of the dynamic power management logic, and that includes clock gating, it includes power gating, it includes sleep states and retention states, everything that's turning on and off dynamically within a particular configuration of the device where it's processing the traffic that in its intended mode. All of that, you need some good representative traffic for that, and that's traditionally been a hard thing to get what we used to call representative vectors for that. These days, with good emulators and other areas, very strong top-level test benches and so on, we can derive some of those traffic scenarios, and those traffic scenarios can be fed to power analysis tools to give us a more accurate but nevertheless iterative look at how power is going to be developing on the device. What makes it more complex, though, is the fact that the power management on the device for the dynamic power is becoming more and more complex. There is firmware that wants to wants to be tuned both for the improved performance given the resources on the device, and at the same time it wants to reduce the power of the device. So that firmware, that power management firmware, is adaptive and can be very, very complex. There's other software at higher levels, even the operating system, of course, that are involved in power management, depending on what domain you're in. And so emulating how that adaptive power management takes place can be very difficult, and we need to try and model it with predictive equations. And those predictive equations in turn can be used by the developers of the software in order to get better results. But the power performance trade-off on devices has become a big issue, and it's something that the software folks need more help with, because we don't want to leave things on the table, obviously. We want to meet those power caps that we signed up to, or that we have to meet due to the thermals or the enclosures and so on. And one of the ways to do that is by helping to tune the software side of the power management. Often the first line of defense there is a processor that's right on the die that is programmable, and it may be sharing its resources for other tasks as well. But we often see now dedicated smaller processors that are just there for power management and also for tuning up performance.
Ken Wagner, thank you very much for a great explanation of some of the problems that you're dealing with.
You're most welcome, Ed. Thank you.